Okay, so I'm continuing with a review. This time I'm going to be looking at regression, and in the previous review videos we've been focusing on the square footage data. In this video we'll be looking at the sample from Queens and examining the relationship between square footage and rent. So I have this data in my calculator. So in list 1 and list 2, in list 1 I have the square footages, and in list 2 I have the rents. So I'm going to start by looking at a scatter plot. So I want to make sure that my plot is turned on, and it is, and I'm using list 1 and list 2, and it is the scatter plot. So I'll look at scatter plot, and what am I seeing here? There is a positive association. So as I look from left to right, there is an upward trend. That makes sense. What that means in this context is that apartments with that are larger rent for more. No surprise there. What's the pattern here? Well, I'd say that this is a fairly strong linear pattern. So let's actually do some calculations to see if we can quantify the direction and the pattern here. So I'm going to go to my stat menu, and this time I'll use a calculation, and I'm going to run a linear regression. That's option 4. I don't have the prompt, so I'm going to have to tell my calculator where my data is. It's in list 1 and list 2, and so I'm finding that I have a regression line of ax plus b, where a is 2.2 and b is negative 34. So I'm just rounding at one decimal place here, and so this would be my y hat. And I've also noticed that r squared is 0.8268 and r is 0.9093. So I'm going to add my regression equation to my scatter plot, my regression line rather. And so I'll go to my function list and type in 2.2x minus 34.3. And then let's go back. Here's the regression line over top of the scatter plot. And yeah, it does a pretty good job of fitting this data. And we see that in the correlation coefficient, 0.9. That's very close to 1, which would be a perfect positive. Let's compare this to a critical value. So for that, I'm going to need to know my sample size. So how many ordered pairs did I use to create this? There were 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the critical value, I'm going to look in a table, and it'll take a few minutes to find that. I'll show it to you. So here is the critical value table. I want to look for 12, and let's see if I can get that to focus a little better. Yeah, so here is for 12. The critical value is 0.576. So 0.576, and that was with a sample of 12. So since R is greater than my critical value, my conclusion is that there is evidence of a linear correlation. And finally, let's see, what can we say about, what does this r squared tell us? So r squared is 0.8268. I'm going to just round this to a little bit more and just say that this is approximately 0.83. And I'll interpret that as saying 83% of the variation in rents is explained by the regression on square footage. And I should say here, the rents for apartments this was in Queens. All right, so now let's use this regression equation. What if we had an apartment that was 2,000 square feet? And we want to say, well, what would be the market rate for an apartment of this size in Queens? So I'm going to evaluate this function and say, the predicted rent for an apartment of this size would be 2.2 times that square footage minus 34.3. So 2.2 times 2,000 minus 34.3. That is, the predicted rent is 4,365.7. Now, is that a reasonable prediction? Something I want to point out here is in our original data, the range of square footage was from, let's see, I think the smallest is this 500, and the largest is the 1452. So 2,000 is not in the range of our source data, and that was the data that we used to construct this regression equation. So I would be hesitant to use this. That would be called extrapolation. So we are trying to make a prediction outside the range of our source data. So this would be used very cautiously. If we were to make a prediction for an apartment with a size of 1,000 square foot, that's well within the range of our source data. And so here we would take the predicted rent would be 2.2 times 1,000 minus 34.3, and 2.2 times 1,000 minus 34.3, and that would give us $2,165.70. Now notice, in the original data set, there was an apartment with the size of 1,000 square feet, and the actual rent there was $2,000. So this is a predicted value, y hat, and then this is an observed value of y, which was 2,000. So the prediction is a little off from what we observed in the source data. That difference is called a residual. So this is would be what we would predict to be the average rent for apartments of this size, and this is a particular rent for an apartment of that size. So lastly, regarding this regression equation, I want to focus on the slope and the y-intercept in this regression equation and how we can interpret those. So 2.2 is the slope, and negative 34.3 is the y-intercept. So what does the slope tell us here? That tells us that for each additional square foot in size, the rent for apartments in Queens increases by $2.2, $2.20. Now, what about the y-intercept? So that's negative, excuse me, negative 34.3. So that would be the predicted rent for an apartment with 0 square foot. That actually doesn't make sense in this context, so we won't interpret the y-intercept here. All right, I hope that helps with an understanding of regression. So we started with a scatter plot, then we looked at the various output from our calculator. We were able to get slope, y-intercept, the coefficient of determination, and the correlation coefficient, we could interpret each of those in context and then use the regression equation to make some predictions. We have to be a little careful in making predictions that we're not going outside the range of our source data. So this one I would make with caution. That's my little yield sign there. And we notice that when I make a prediction that's for something inside that data range, I actually got a pretty good result, something very near one of the observed values. All right, until next time.